Hi everyone, this is Tintin. Today we'll present my final project in computational physics about the galaxy classification with decision tree and random forest classifiers. So first I want to introduce to you about the Sloan Digital Sky Survey, where the galaxy images I use in the project came from. SDSS galaxy observations have been crucial in our recent understanding of the origin and evolution of galaxies, and personally, something that really excites me is their map of the large-scale structure of the universe, which supports our current cosmological model involving cosmic inflation, dark matter, and dark energy. And having millions of galaxy observations is amazing, but it's simply too much data for small group scientists to classify. So the Galaxy Zoo project was created to mobilize volunteer citizen scientists to help classify galaxy images based on a given classification guide. And this is great because types of galaxies with consistent majority vote are generally really reliable. And also this project provides an immense data set to help train machine learning galaxy classifiers for future uses. Here is a galaxy classification guide provided by the Galaxy Zoo project. In my project, I focus on distinguishing between smooth and disk galaxies, which can be further divided into subgroups based on the roundedness, the central bulge, and the spiral arms properties of the galaxies. And overall, I was classifying over 20,000 galaxy images into 10 different subgroups. So now that we are motivated by the galaxy classification problem, I will briefly introduce the concept of decision tree. So imagine you taking first grade geometry and you're asked to classify the shapes given on the slide, and you can think of sides and angles, properties like if a shape has equal sides or if there is 90-degree angle, and make a decision on what shape it is. And this is similar to how we feed certain features to train the decision tree so that it can make a classification guide for these shapes. And then you're given the geometry exam and boom, you're gonna ace it based on the side and angle features. But you can imagine if you try to classify these shapes based on misleading features like color and border thickness, you might be misled to think that this is a regular triangle because the given regular triangle is brown and this is also brown, or you're so misled into thinking this is a rectangle because it has a thick border like the rectangle shown in the training data set. So bottom line is extracting the right features are super important. And this is the main challenge I encountered in my project, how to extract the right features from raw optical galaxy images. When we have a nice decision tree, we can combine a couple of them, which might have different ideas of how to classify things, to do a majority voting to maximize the accuracy of the predictions. And this democratic method is called a random forest. So mentioned earlier, extracting features from raw data image is really important. So first I have to do some image processing so I can identify the rough shape of a galaxy from the raw images. And then I'll start extracting some geometric and photometric features, and I'll discuss some important ones briefly here. First, we have eccentricity from 0 to 1. As the eccentricity increases, you go from a perfectly round circle to a very elongated ellipse. Form factors and other important features defined as area per perimeter squared, which is important in elliptical galaxies, which has a great area bounded by a small perimeter. And important photometric features include the mean intensity showing you the overall brightness of the galaxies and the central light intensity showing you the existence and shape of the central bulge. In the data set I was working with, each galaxy images came in 3 color bands, G, R, and I. So I can also look into the differences in the light intensities of each of the 3 bands. And finally, the Gini coefficient provides a measure of the inequality of the light intensity distribution of a galaxy image. And you might have heard about the Gini coefficient in describing the inequality of a country's economy. So you look on this plot, this straight line y equals x describes a perfectly equal utopian society where 50% of the population owns 50% of the wealth, 20% owns 20% of wealth, and so on. And the deviation from this perfect straight line measured by the area between the bounding curve give you a sense of the quality of a society. And same applies for galaxy images, where you just have to replace the population with image pixels and wealth with light intensity. So I've extracted and played around with roughly 40 different features and look into whether they are important or irrelevant. I decide on using about 20 of them. And you can see from this graph, eccentricity, form factor, and Gini coefficient are overwhelmingly important in overall galaxy classifications, followed by information involving light intensities. So now that I'm satisfied with all the features I extract from raw images, I combine different decision trees to form random forests. I ran different tests to fine-tune different parameters of a random forest. And here I'm showing the most important parameter, which is just simply the number of decision trees in the random forest. And I started from a single decision tree with a 56% accuracy. And after combining 20 or more decision trees, the predicted performance rises by about 13%, which is impressive. So after trying to classify all galaxies into 10 subgroups, I started to do a deep dive analysis into each layer of the classification scheme, starting from distinguishing between disk and smooth galaxies, which the random forest classifier does a great job of 85% accuracy. On the left plot, you can see something called confusion matrix, that the classifier can predict accurately 78% of the time for disk galaxies and 90% of the time for smooth galaxies when we read out the diagonals of the matrix. And on the right feature important plot, you can see that the Gini coefficient and R minus I difference are the most important features in this case. So it's interesting to point out that it's the photometric features, not the geometric features, that play the most important role in distinguishing between disk and smooth galaxies. So to further investigate these two features, I plot normalized histograms of intensity difference R minus I and Gini coefficient among disk and smooth galaxies. And on the left plot, you can see that the smooth galaxies denoted in blue have consistently high intensity difference R minus I. And on the right plot, you can see that the disk galaxies denoted in red have consistently higher Gini coefficient, meaning they have more unequal light intensity distribution. And you see the two histograms of these two galaxy types distinguishing themselves very clearly, which makes these two features nice one to distinguish between disk and smooth galaxies. So similarly, I'll look into the next classification layer among smooth galaxies, which can be further divided into 3 subgroups: completely round, in between are cigar-shaped, and the random forest classifier has an impressive 89% accuracy rate. And you look at the right feature importance plot, eccentricity and form factor, the geometric features, play a really important role. And that's not surprising because round galaxies have lower eccentricity, while cigar-shaped galaxies have really high eccentricity due to the elliptical nature, and the in-between galaxies literally lie in between. And on the right graph, the form factor, it shows an opposite trend because the round galaxies have higher form factor due to having greater area bounded in smaller perimeter. And finally, I want to discuss the disk galaxies with phase-on inclination case, where it can be further divided into 4 subgroups based on the spiral arms: no spiral, tight, medium, or loose spiral. And when you look at the confusion matrix, it's really interesting that the algorithm tends to put everything on the first class, which is the no spiral galaxies group. And I note that no spiral galaxies form the majority of this subgroup. So the algorithm is biased towards predicting that an unknown galaxy belongs to the majority class, which is no spiral in this case. And it makes sense because random forest classifier wants to maximize the overall accuracy, so it tends to put things in the overwhelmingly popular class because you get it right more often than not. But here it struggles with a 60% accuracy. And if you look at the feature importance, the only distinctive feature is the R minus I difference, which is not really overwhelmingly a distinctive feature if you compare to previous case, though this is another reason that the classifier struggles in this case. So here's a summary of the conclusions from my project. Possible next steps include addressing the bias towards a majority type, as recently mentioned, and finding better classification features for spiral galaxies. And finally, I think it would be interesting to run this classification model on a convolutional neural networks and compare the predictive performance with the random forest classifier. Here's a list of reference used in the project and some acknowledgement to the galaxy image from SDSS, Galaxy Zoo, Astro NN Python package, Kaggle Galaxy Zoo Challenge contestants for sharing their ideas, and Professor Kenneth Johns, who's teaching the computational physics class, for valuable suggestions and feedbacks. Thank you so much for listening.